Good afternoon, everyone. I appreciate the opportunity to present this technology to you, and also, thank you for attending. Microplastics is a very hot topic nowadays, and generally we're considering microplastics as being particles from 1 micron to about 5,000 microns. I recognize 5,000. You can obviously see it, so it would require a different kind of measurement to do the analysis. The area that we are generally interested in is between 300 microns and 10 microns. Now, the interest in microplastics has really been increasing here recently, especially since some studies have revealed that microplastics are inside our bodies, inside organs. They've found them inside arterial plaques and so on. Now, we're not exactly sure, what they can do, but in terms of the damage they can do to the body, I mean, they are vectors for various other kinds of pollutants. And if you follow the old adage, likes like, well, microplastics are organic. And so, other things that are organic can hold on to them and cling on to them, that is. And so those are the kinds of things that we're really concerned about. Right now, there are no real standard methodologies for analyzing microplastics, although, with the ASTM and the Southern California Coastal Water Reclamation Project have developed some methods, ISO as well. So we certainly are making progress, especially on this side of the Atlantic. In the U.S., we've been a little bit behind, but I believe we're starting to catch up quite a bit. Now, the various techniques that can be used to analyze them really depends on the size. Initially, and this is actually still done, manual microscopy is just strictly a by-eye approach. It's definitely subjective and inaccurate. We have wet chemical methods, and including GCMS and pyrolysis and so on. These tend to be physically intensive, and it can be difficult for small type particles, and they're very destructive. And then finally, the topic that I'm going to be discussing in this presentation is molecular spectroscopy, specifically infrared. These kinds of techniques are chemically specific. You can get particle identifications very easily. They're non-destructive. They can be highly automated. Unfortunately, there is a high sample preparation requirement. In order to do an effective job with the analysis, got to get the sample down to the bare particles, which of course will require some fairly extensive procedures to purify the samples. Now, what is it about infrared? Infrared is a vibrational spectroscopy technique. Essentially, the samples are exposed to a source of infrared radiation, and at the characteristic vibrational frequencies of a particular sample, they will absorb that radiation and producing a peak. And now a molecule might contain, different atomic combinations. And so each atomic combination will have its own characteristic vibrational frequency. And the set of frequencies then will give us an infrared spectrum. Now, the beautiful thing about it is that the molecules will each have their own characteristic infrared spectrum, and from that we can compare the spectrum that's collected to a spectrum in a library. And because infrared spectroscopy as a technique has been around for a very long time, we have very extensive libraries to do that comparison, so we can do a very good job identifying microplastics. Now, to analyze a microplastic sample, it is micro, so it could be pretty hard to see with the naked eye. And so what we would need to do then is to use an infrared microscope, which allows us to view a sample under high magnification, reduce the infrared beam down so that it matches the size of the particle, and then collect an infrared spectrum. Now, the drawback of this technology, well, you get a nice infrared spectrum. The drawback is that it's labor intensive. The data can be seriously impacted by operator bias / operator variability. So it's very hard to be extremely precise doing this kind of measurement. The overall operation and the workflow would tend to require significant experience, thereby making the learning curve somewhat steep and long. And as well, it can be very time consuming. So recognizing that, Agilent developed a workflow for a laser direct infrared system that automates essentially the entire analysis. The software itself is very intuitive. It's icon driven. There are no real menu items that one would have to learn. Provides very good characterization of microplastics, pharmaceutical tablets, and other kinds of material samples. Has the ability to analyze very large sample areas and then explore smaller areas of interest with a lot of detail without having to change over any optics or anything. And then there's no requirement for liquid nitrogen, which for traditional infrared microscopes, due to the kinds of detectors that are being used, liquid nitrogen is needed for their operation. So it really simplifies maintenance and keeps the environmental health and safety department somewhat happy. Now, some of the traditional operations that are required would be, locating the sample. You might use a joystick or something. You might have to change magnification, require rotating the turret, manually adjusting focus, and so on, adding liquid nitrogen, like I've already mentioned. All these things, require some kind of technique. The person really needs to be trained in using the overall instrumentation in order to collect high quality data. So this system, the LDIR, really is a pretty simple device. It has a quantum cascade laser, which was developed internally by Agilent, is made by Agilent, and it focuses all the laser light on a particle. And so there's no need for any kind of manual adjustment of an aperture, an area defining aperture, or anything like that. The area that is illuminated is just the wavelength of the laser. It's rapidly tunable across the mid-infrared fingerprint region. It covers the region from 1800 wave numbers down to around 975 wave numbers. And if you relate to wavelengths, that would be 5.5 microns to about 10 microns. So I talked about sample preparation. The cleaner the sample, the less stuff you have to do, obviously. So as you move to dirtier and dirtier samples, you have to do more extensive sample preparation. So the overall schematic might look like this. Dirtier samples require organic matter removal. And by organic matter, I'm talking about proteinaceous or cellulosic type material. Might have to separate out some sediment. Then the final operation then is filtering. So with our system, what you can do is analyze directly on a filter. There's no transfer of the particles, from a vial, which is a suspension of the microplastic particles. You can just directly filter out, analyze directly on the filter. And as you can see here on the right, you can see some particles here. It color codes as the analysis proceeds. The workflow looks like this. Simply insert the sample. The system will go through, it'll locate the particles, acquire the infrared spectrum, compare the spectrum to a library, and update statistics as the analysis proceeds. Now, as part of this process in locating the particles, it also it will take an infrared image. We'll also take a visible image if that's required, but it'll measure various physical parameters that will give the user an idea and give them some numbers to allow the user to quantify the morphology of the particle. And it repeats this for every single particle. Now, if we go to statistics, it'll classify the particles then according to size. It will look at the individual particle size, particle classifications versus the numbers. It will analyze the percentage of each individual polymer relative to the entire sample. So we start out with a visible image. It will analyze a region of interest using what we call discrete frequency mode. And so this is a single wavelength. So it illuminates a region of interest with a single wavelength. When that light hits a particle, that particle absorbs some of the light, thereby illuminating itself essentially, and the system will remember what the coordinates are. It will go back then and it will collect a full range infrared spectrum. And that's the spectrum collection at that point is what we call sweep mode. And as you can see here, the solid line is the library spectrum. The solid line is the infrared spectrum of the sample that was collected, and then the dashed line then is the library spectrum. And so essentially it just matches up the peaks, and it does its identification. As part of that, we get a hit quality index. So that tells us statistically how well the collected spectrum matches that of the library. And by statistics, okay, as I mentioned before, it first off, it color codes each individual polymer. And so if we hop back here, okay, we can see some different colors. Actually, we'll step one more back. Right here, you can see some individual colors here. Each individual color represents a particular plastic that was identified. Okay, and so it'll take these color-coded polymers and it'll tell us the numbers of each one of those, also the percentage relative to the total number of particles that was detected. We get an idea of the group sizes and the particle range versus the count, and also particle diameter versus the count. Finally, a data table will be provided, which gives you all the different parameters that have been analyzed: width, height, diameter, aspect ratio, area, perimeter, eccentricity, circularity, solidity, finally, the identification of what the polymer is, and whether or not it's a very good match. So the system really automates the entire particle analysis workflow, and especially for environmental labs, this comes as a big benefit because environmental analysts have a ton of techniques that they need to learn how to use, and the last thing they need is one more technique to gain expertise in. This really simplifies using molecular spectroscopy for the identification of microplastics. So with that, I thank you very much for your attention. I'd be happy if I have time to answer a couple of questions.
We do have a couple minutes. So if anybody has any questions, yeah, feel free to drop them in the Q&A or in Whova. We do have a comment from one of the attendees thanking all the speakers in this session, saying that it was very cool.
Oh, good.
All right, well, if we don't have any questions, oh, here we go.
Fantastic.
Right. I can go ahead and read that one. It says, did you try other membranes like L203?
L203. Okay, so I didn't mention this in my presentation, but the kinds of filters we use, it needs to be, the system operates in reflectance, and so we need a reflective substrate. The filters we use are 1 inch in diameter, and they require a reflective film, and so we use gold, aluminum, or silver. The pore size is about 0.8 microns, and the thickness of the metallic layer is about 100 nanometers. The actual material, the support material, is polyethylene terephthalate, but the particles don't make contact with the membrane.
We have a couple more questions, Sarah. Do we have time for those?
We could probably take one or two if they're yeah, these ones seem fine. These last two questions I think we can take, and then we have 3 now.
Okay.
Oh, good. That's good. I'm happy about that.
The first one is, what challenges do you see in operating this in remote areas?
Yeah. Okay. So you just need a source of electricity. It's stable, and so you don't need to put it on an air table or anything like that. But it requires a clean air, or actually I should say dry air, dry nitrogen purge to operate. So that would really be the only challenge. And so I would say if you have a source of electricity, then you can have a generator for the purge. And so that would really be the only challenge.
Okay, great. And the next one is, what is the lowest size particle that can be accurately detected?
Right. These are infrared wavelengths. Okay. And so our longest wavelength is 10 microns. And so that would be the lower limit. It would be 10 microns. The sweet spot for the system is between 20 and 500 microns, but we can definitely generate data, collect data, that is, from 10 micron size particles.
Okay, great. And then the last question we have here is, can you say how this is different from FTIR analysis in terms of pros and cons?
Yeah, okay. It is an infrared analysis. There are 2 general types of infrared systems that would be used. I should say 3. One would be a manual infrared microscope. Second one would be an automated single point infrared microscope, and the third one would be an an infrared microscope fitted with a focal plane array camera. Okay, infrared, advantages of infrared, it's going to cover a very broad wavelength range, covering the entire infrared spectrum from 4,000 wave numbers probably down to 700 wave numbers. This is using a quantum cascade laser, so we cover most of the mid-infrared fingerprint region from 1,800 to 975 wave numbers, which is a region where most of the peaks occur that you need for identification. And so probably a slight advantage of the infrared, the FTIR at that point would be it has a broader region of collection. Disadvantage of infrared is that the source is weak. It is just it's an omnidirectional source. It's just a black body emitter, incoherent radiation, and so the signals tend to be pretty weak, which is really could really reduce the sensitivity of the measurement. It's going to take a little bit longer. Most infrared systems require a lot more expertise to do the analysis. So the training curve is going to be somewhat steeper and definitely much longer. Now with single point systems, they require the use of an aperture, and so you have to be able to adjust the aperture around each individual particle, and so at that same time you have to collect another background, so it's a little more complex. There's a lot more steps to follow, again, with a traditional infrared system. And then finally, with a focal plane array system, you're not using a area defining aperture. You can take a snapshot over a broader region and get thousands and thousands of spectra at once, and so you have to go off and sift through all those data, all the spectral waste to get to the individual microplastic particles. So I tried to go through that pretty quick, and I probably missed some things, but in a nutshell, I think that about covers it.
So that was pretty thorough. Great. Thank you so much.